Hello students. So we start with the second module, that is spectroscopic techniques and applications. In this module you will be studying how we can do chemical analysis using some spectroscopic techniques. Now spectroscopy is defined like this: study of the interaction of electromagnetic radiation and matter. Okay. So when a radiation falls on matter, the radiation and matter will interact, and due to this something happens to the radiation and something happens to matter also. So if we study that, then we can understand something about matter. That is, we can do chemical analysis. Now, this is not done using our naked eye. We cannot study this with our naked eye. So for that, we have to use some instruments, and that instrument is called a spectrometer. The instrument which is used to study this interaction is called spectrometer. The result of this interaction comes out in the form of a graph. Okay, something is plotted against something, and that graph is called spectrum, the graphical representation of interaction of matter and radiation, that is called spectrum. So these are the three important terms in this topic. Okay, spectroscopy, spectrometer, and spectrum. Moving on to electromagnetic radiations. So this is an electromagnetic radiation. It is represented like this in the form of a wave, and electromagnetic meaning it has an electric component, the red one, and it has a perpendicular magnetic component, the blue one. So this electromagnetic wave can be defined using some parameters. You have already studied that in your lower classes. One is frequency, nu. Unit is hertz. So frequency is the number of oscillations per second. Then you have another term, the wavelength, lambda, which is expressed in nanometers. So wavelength is a distance between two crests or distance between two troughs. Or in other words, we can say it is a distance traveled by a single wave. The wave starts from this point, it reaches a maximum, comes down to a minimum, and then finally when it comes to the base value, the distance traveled by that is the wavelength. And if you take the reciprocal of wavelength, you get the wave number, that is nu bar, and nu bar is measured in centimeter inverse. Then you have the height of this wave, that is known as the amplitude, or another word is intensity. So these are the different terms with which you can define this electromagnetic wave. What is the relation between these terms? Frequency, wavelength, and wave number. What is the relation between them? So nu is equal to c by lambda, where c is the velocity of light, and 1 by lambda is equal to nu bar. So these are the two relations. Nu is equal to c by lambda, and 1 by lambda is equal to nu bar. The value of c in centimeter per second is 3 to 10 raised to 10. Okay, why we are taking centimeter per second, we will see that later. So how will we write the expression for energy of this radiation in terms of frequency, wavelength, or wave number? So this is the expression: E is equal to h nu, that is equal to hc by lambda, is equal to hc nu bar, where h is called the Planck's constant. Planck's constant, and the value of h is 6.636 into 10 raised to minus 34 joule second, or another unit is kilogram meter square per second. So this is the expression for energy of a radiation. Coming on to matter, matter also possesses some energies. Okay, matter also possesses some energies. So we will see what are these energies. The first type of energy is called translational energy. If you look at this animation, you can see matter, a molecule. Let us assume a molecule. The molecule can move along any one of the axes, x, y, or z axis. That is called translational motion, and the energy associated with the translational motion is called translational energy. Other than translation, a molecule can rotate about a particular axis like this. It can rotate about an axis, and that is the rotational energy. Other than rotation, the atoms present in a molecule can vibrate along the bond length like this. It can vibrate along the bond length, that is called the vibrational energy. So these three are the energies for the whole molecule as such. Okay, within the molecule, if you are looking, then it has electronic energy. The electrons, they can absorb energy and they can move from one point to another inside the molecule. And it also has nuclear spin energy. The nucleus can spin. Okay, so that also produces some energy. So these are the different types of energies present in matter. Now quantum mechanics tells us that, before that, all these energies are affected by radiations. If you allow the radiation, a particular radiation, to fall on matter, then it can change these energies. Like rotational energy can be changed using microwave radiation. Vibrational energy changes using IR radiation. Likewise, each energy can change when we send a particular radiation. So quantum mechanics tells us that energy is quantized. So if you are plotting the different energy levels, energy values, then you will get a diagram like this. These are the translational energies. Okay. Then these are the rotational energies. Each line represents one energy value. These are the vibrational energies. And finally, these are the electronic energies. So if a molecule is rotating with this particular energy, it can absorb some energy and it can go and start rotating at this level. Okay, it cannot take a value in between. It cannot take a value in between. So that is a meaning when we say that energy is quantized. So let us consider two energy levels, E1 and E2. It can be anyone. It can be either electronic or vibrational or rotational, whatever it is. The difference between these two energy levels is delta E. So delta E is equal to E2 minus E1. Now let us assume that a chemical species, can be a molecule, it can be atom, anything, a compound, anything, it is sitting in this lower energy level. So this species or this chemical entity has to absorb an energy equal to delta E. equal to delta E if it wants to move from this energy level to this energy level. Okay. So suppose we are sending in a radiation which has an energy equal to delta E. So what will happen? This species will absorb this and it will go to the higher energy level. Now this process or this type of spectroscopy is called absorption spectroscopy. Absorption spectroscopy. So here the radiation gets absorbed. Now suppose you consider the opposite case, the reverse case. The chemical entity is sitting in a higher energy level. It wants to come to the lower energy level. That can be done by releasing or emitting a radiation like this. It comes to the lower energy level and it emits a radiation. And this is called emission spectroscopy. Emission spectroscopy. So spectroscopy can be classified into two categories: absorption spectroscopy and emission spectroscopy based on the radiation. Okay, if the radiation is absorbed, it is called absorption spectroscopy. If the radiation is emitted, it is called emission spectroscopy. So there are two types of spectroscopic techniques. This process of changing energy level, that is either from lower to higher or higher to lower, both, it is commonly called as a transition. Transition. So we will be using this word in our future discussions. Okay, so transition means change in energy level. Now in terms of matter, how can we classify spectroscopy? That is what we are going to see. So you have matter, so something, either an atom or a molecule, and that is absorbing or emitting. It can absorb or emit a radiation. So if this chemical species that is absorbing or emitting, if it is an atom, then that technique is called atomic spectroscopy. Atomic spectroscopy. Okay. Whereas if the molecule as such is absorbing or emitting, then that technique is called molecular spectroscopy. Molecular spectroscopy. So based on matter, we can classify spectroscopy into two, that is atomic spectroscopy and molecular spectroscopy. So combining these two, let us see. Spectroscopy is classified into absorption and emission spectroscopy based on the radiation, whether it is absorbed or emitted, and atomic and molecular spectroscopy based on whether atoms or molecules are involved in this technique. Okay. So if you combine these, we will get four different techniques. Four different techniques. What are they? Atomic absorption, atomic emission, molecular absorption, molecular emission. These are the four techniques that we are going to get. So we will be discussing about molecular absorption spectroscopy only, because our syllabus is restricted to that only. So we will be discussing molecular absorption spectroscopy. Now what are the advantages of spectroscopy? Compared to normal chemical analysis like salt analysis, you might have done salt analysis in your lower classes. You might also have done titrations in your lower classes. Salt analysis, you are identifying the components present in a substance, is it? What are the ions? What are the cations? What are the anions, etc. Titration means you are quantitatively finding out. You are finding out what is the concentration of a particular substance. Okay, so this will take some time. Salt analysis, it will take some time, isn't it? Titration, that also takes some time. Okay, and you have to be very careful while doing titration. In one drop you should get the color change. So here in spectroscopy, if you are using spectroscopy, there are some advantages, like it is more reliable. Okay, it is more reliable because the instrument, you are using instruments, and if the instruments are properly working, then it is more reliable. Then more accurate, you will get more accurate results compared to direct estimations. Thirdly, wider applications. Okay, there's wider applications, then less time is required. You require only very little time. Like if you want to find out what are the components present in a particular substance. Okay, like you are given, let us say, magnesium chloride. You want to find it out. In that case, you can do with this technique in very short time, maybe 10 to 15 minutes. You can find it out. The other way, if you want to do chemical analysis, salt analysis, it will take about 2 or 3 hours. Okay, so less time is required, then less quantity. You require only very little quantity. Whereas in normal salt analysis or titrations, you require some quantity. Even that much you don't require here. Non-destructive method. Non-destructive means after doing the analysis, you can take back the sample. Whereas in normal salt analysis, if you see, then after you complete the salt analysis, the entire sample will be over. Even titration, you titrate an acid and a base. After doing the titration, you cannot reuse that thing. That acid and base is lost. Okay, so they are destructive methods. This is a non-destructive method. So these are some of the advantages of spectroscopy. Now we will move on to the techniques, the different techniques. Our syllabus specifies 3 important techniques: electronic, vibrational, and NMR spectroscopy. So one by one we will be discussing those.